66 million years ago, during a typical spring day in the era we now term the Cretaceous, a massive rock comparable to a mountain barreled toward our planet at 20 kilometers per second. For eons it had journeyed silently through the icy void of space, its path influenced by an endless series of gravitational forces, from Jupiter's mighty tug to the gentle prods of drifting comets and the subtle tilt of its own rotation. All that backstory now faded into irrelevance. What truly counted was this. In about 4 hours, the 10-kilometer-wide orb of carbonate and iron would slam into the shallow waters near the Yucatan Peninsula, as we know it today, forever altering the course of life. The collision unleashed power, equivalent to 100 million atomic bombs. It incinerated countless billions of tons of stone, sulfur, and ocean water, hurling a vast plume of particles high into the upper atmosphere where it would encircle the world in mere hours. Flames raged unchecked over entire land masses. Towering waves, hundreds of meters tall, battered shores thousands of kilometers distant from the crash site. Soon after, an endless gloom descended, a prolonged dimness, lasting a full year as sunlight was blocked by veils of dust and sulfur particles, plunging worldwide temperatures by almost 30 degrees Celsius. Vegetation perished first, starved of light for photosynthesis, followed by the plant-eaters reliant on them, and then the carnivores that preyed on those herbivores. In the blink of a geological eye, 3/4 of Earth's species vanished. Among them every dinosaur bigger than a domestic feline. That's the record etched in the rocks. A slender band of iridium-laden clay, defining the divide between the Mesozoic and Cenozoic periods, linked to the 200-kilometer-wide wound hidden under Yucatan sediments. Yet this evening, let's envision an alternate path. Suppose that celestial boulder, that sky-falling behemoth, had veered just off course. It almost did, in a sense, since any cosmic body's flight hinges on myriad factors from billions of years prior, and tweaking even one could yield a wholly different result. Certain experts have modeled scenarios where the Chicxulub impactor arrived mere minutes sooner or later, hitting the open ocean instead of coastal shallows. That would mean far less pulverized stone, reduced sulfur lofted skyward, turning a worldwide apocalypse into a mere local disaster. The dinosaurs would have stirred the following dawn in a rattled but intact realm. They might have pressed on, ruling every land-based habitat, just as they had for the prior 165 million years. Now settle in and allow the present era to dissolve. Hear the whisper of breezes among Cretaceous foliage. Sense a planet bracing to endure, not expire. This tale unfolds the 66 million years that fate bypassed, and we'll trace its every twist side by side. Uncovering the asteroid's role in the dinosaur's demise is a captivating saga in its own right. It's a prime example of science in action, how an outlandish theory, initially scorned as mere speculation, gains traction as proof piles up. Back in 1980, physicist Luis Alvarez and his geologist son Walter were probing rock layers around Gubbio, Italy, scrutinizing that slim clay stratum at the Cretaceous-Paleogene edge. They spotted an anomaly. Iridium in abundance, 30 times above average levels. This metal is scarce across Earth's crust, having mostly plunged to the core during the planet's fiery youth. Yet it's plentiful in asteroids. The Alvarezes suggested a colossal strike had coincided precisely with the dinosaurs' exit, and they forecasted a telltale crater lurking somewhere on the globe. Skepticism ruled the day among scientists. Plenty of geologists leaned toward volcanic culprits, pointing to the Deccan traps in India, which spewed lava for millions of years right then, blanketing half of today's India under kilometers of basalt. That alone, they argued, could account for the die-off. Undeterred, the Alvarezes amassed more data, while fellow seekers scoured for the impact site. As early as 1978, geophysicist Glenn Penfield had detected an irregularity during an oil survey in the Yucatan. A huge ring-shaped feature concealed under surface layers, detectable solely via gravity and magnetic surveys. Its nature eluded him, but he wondered if it might be a meteor crater. It wasn't until a full 10 years later that the pieces finally fell into place, with rock samples pulled from Mexican oil drills revealing shocked quartz and tektites, materials that only crystallize amid the immense forces of a meteor strike. Come 1990, the evidence sealed the deal. The crater existed, dated precisely to that fateful time, and measured just large enough to trigger the mass die-off. Yet, here's the key insight that opens the door to our hypothetical scenario. Asteroid collisions aren't fated events. They're not written in the stars, they're sheer happenstance, driven by the intricate dance of orbits and subtle tugs from gravity across eons so immense that the results feel utterly unpredictable. The Chicxulub projectile might have hit mere minutes sooner, plunging into the ocean depths. Or it could have shown up hours later, slamming into the Pacific's heart. Or perhaps it bypassed our world altogether, hurtling onward through space toward the distant reaches of the solar system, gone forever. In any of those alternate paths, the dinosaurs endure, not through some predestined luck, but simply because the catastrophe that ended them never takes place. That's where our tale kicks off. The space rock tears into the atmosphere, blazing a fiery streak overhead, spotted from over 1,000 kilometers distant. It crashes into the Pacific, some 2,000 kilometers offshore from the closest shore, unleashing colossal waves that ravage shorelines throughout the Americas and Asia. Countless animals perish, habitats shatter and take years to rebound, yet the sulfur remains submerged. The debris clears in mere months, not dragging on for ages. Sunlight persists undimmed. Vegetation thrives uninterrupted. And the dinosaurs, tyrannosaurs prowling, triceratops grazing, hadrosaurs trumpeting, ankylosaurs armored, all persist in their long dominion, feathered maniraptorans flitting through the foliage as before. For them, the crisis barely registers. They've weathered harsher blows, the choking ash clouds from Deccan floods of lava, the creeping chill of the waning Cretaceous, the relentless drift of land masses, and ebb of ancient waters that have remolded their realm across millions of cycles. As the pinnacle of terrestrial megafauna, they've dominated like no other lineage, with no hint of fading. Their variety peaks now. Forms span from pint-sized bug hunters the size of chickens to lumbering plant-eaters tipping the scales at 40 tons. They fill every habitat, from frozen boreal woods to steamy jungle mires. For 165 million years, this has been their domain, and nothing in evolution suggests they couldn't stretch that run another 165 million. Dinosaurs rule the Earth, and for the first time ever, we're about to witness their potential mastery of it. To grasp the possibilities, though, we must first confront the reality. Pull away from this budding alternate timeline and examine the true inheritance the dinosaurs would have carried forward. Ditch the kid-lit caricatures. Skip the blockbuster beast flicks. Instead, confront the authentic late Cretaceous globe in its full, bizarre intricacy. shrug off those imagined scorched wastelands. 66 million years back, the planet buzzed with lush vitality, far balmier and sodden than our current setup. Polar ice sheets, non-existent. Oceans lapped about 170 meters above today's baselines, flooding lowlands and carving continents with vast, shallow interior waters. North America split into twin landmasses, cleaved by the balmy western interior seaway that ran from the Gulf of Mexico up to the Arctic. India floated as a rogue isle, inching toward its destiny against Asia. Australia hugged Antarctica tight, both draped in mild woodlands. Even the atmosphere felt alien. CO2 concentrations may be quadruple today's, oxygen a touch richer, the whole setup trapping heat equator to equator. Alligators roamed past the Arctic Circle. Woods flourished where Antarctic glaciers now scour the rock. Polar ice sheets, non-existent. Oceans lapped about 170 meters above today's baselines, flooding lowlands and carving continents with vast, shallow interior waters. North America split into twin landmasses, cleaved by the balmy western interior seaway that ran from the Gulf of Mexico up to the Arctic. India floated as a rogue isle, inching toward its destiny against Asia. Australia hugged Antarctica tight, both draped in mild woodlands. Even the atmosphere felt alien. CO2 concentrations may be quadruple today's, oxygen a touch richer, the whole setup trapping heat equator to equator. Crocodiles and their kin roamed north of the Arctic Circle. Lush woodlands thrived in spots now buried under Antarctica's massive ice layers scraping the underlying rock. Dinosaurs occupied nearly every habitat on land that you can picture. Our clearest glimpse into this lost era comes from the Hell Creek Formation, a vast rock stratum spanning Montana, the Dakotas, and Wyoming. It captures the final 3 million years of the Cretaceous period with a stunning clarity. Excavations by paleontologists, there yield more than scattered fossils. They uncover a full snapshot of a vibrant biological community. Etched into the rock, we can piece together this whole ecological system with impressive accuracy. At the top of the food chain stood Tyrannosaurus rex. It's essential to envision this creature as it truly existed, far removed from the sluggish, dragging-tailed depictions of past illustrations, and instead as a creature of sheer horror and elegance. Stretching 12 meters from nose to tail tip, this 9,000-kilogram beast of sinew and skeleton, balanced on powerful limbs crafted for sudden bursts of speed, not endurance. Its massive head could engulf a person entirely. Armed with banana-sized teeth, every tooth featured jagged edges like a butcher's blade. They sliced through bone effortlessly, much like you'd crunch into a piece of fruit. Yet the standout trait was its gaze, with eyes positioned forward in a streamlined skull that tapered at the nose. T-Rex enjoyed overlapping fields of view. This binocular setup provided keen depth judgment, uncommon in its reptilian relatives. Research by vision expert Kent Stevens determined that its sharpness surpassed that of today's eagles, allowing it to detect potential meals from 6 kilometers off, with distance-sensing skills rivaling the finest in animal history. Far from a mere opportunist scavenging corpses, this was a supreme hunter equipped with elite tracking senses. Still, T-Rex represented an outlier among the meat-eaters. The Hell Creek environment sustained various predators, each adapted to specific roles. There were pint-sized tyrannosaurs, possibly teaming up for hunts, dromaeosaurids boasting their signature curved talons, and troodontids, those odd, big-eyed stalkers whose brain-to-body ratio outstripped all other dinosaurs. We'll revisit the troodontids shortly, as they play a pivotal role in our tale. For the moment, simply register their presence. Compact, clever beings observing everything through unusually perceptive eyes. The plant-eaters showed even greater variety. One species towered over the rest in sheer dominance, its significance almost impossible to exaggerate. Enter Triceratops. According to paleontologist Robert Bakker, its remains accounted for about 56% of all major dinosaur finds from late Cretaceous North America. If that's anywhere near right, it demands a total overhaul of how we view that prehistoric terrain. Imagine the vast prairies prior to European arrival, blanketed in endless buffalo herds that shook the earth with countless pounding feet, where journeys spanned days amid nothing but endless pasture and forages. Now swap out each buffalo for a 9-meter-long, 3-horned behemoth, tipping the scales at up to 9,000 kilograms. Its head comprising a third of its total length, equipped with spears that could impale a T-Rex, and a hefty bony shield guarding its throat. That's Triceratops, the Cretaceous stand-in for the mighty bison, but clad in defenses, fit for a battlefield warrior. Sharing the space with Triceratops were the hadrosaurids, those duck-billed giants featuring extraordinary tooth arrays. Rows upon rows of meshed grinders, perpetually renewing, perfect for pulverizing fibrous plants in ways unmatched by fellow dinosaurs. Then came Ankylosaurus, the living tank swathed in armor plates known as osteoderms, its tail capped by a knobby bone mace that could snap a foe's limb in one devastating blow. Pachycephalosaurus brought its thickened skull dome, likely employed in battering duels akin to those of contemporary rams, although experts continue to debate the point. Countless smaller types rounded out the mix, each carving out its spot in the web of life. Petite ornithopods nibbling low foliage, oviraptorosaurs guarding their clutches. Diminutive mammals darting through the forest floor debris after dark. Soaring overhead were the pterosaurs. Hold on a second, though. These weren't dinosaurs at all. They formed a parallel branch on the family tree, akin to distant relatives rather than close kin. The grandest was Quetzalcoatlus, inspired by the Aztec deity of the plumed snake. When I say its wings spanned 11 meters, I want you to truly visualize it. Broader than a modest aircraft and outsizing every aerial creature from before or after its time. Upright on 4 limbs, it could peer level with a giraffe. However, its skeleton was filled with lightweight, air-filled chambers, making this massive flyer comparable to a light plane in size, weighed just around 250 kilograms. Lighter than plenty of grown humans. It likely pursued prey, stealthily, gliding over vast river valleys with wings tucked close, then grabbing small reptiles, warm-blooded creatures, and aquatic life, using a bill as long as a person's forearm. Now consider those mammals. They were present from the start, developing in parallel with the dinosaurs from the outset, coexisting on the globe for more than 150 million years. Yet they stayed diminutive. The biggest mammal from the Cretaceous era might have matched a badger in scale. The majority resembled rodents like mice or rats, scurrying in foliage, scaling branches after dark, and foraging for bugs and nuts in the overlooked corners beneath the colossal beasts. These weren't flops. They thrived in their roles. Still, survival meant avoidance. They filled slots the dinosaurs ignored. The night-active realm, underground habitats, or minuscule bug-eating territories. All other spaces went to the dominant saurians. Picture the scene that fateful dawn when the cosmic boulder veered off course. A realm of balmy plenty, shifting landmasses and expansive inland waters. Packs of carnivorous theropods chasing herds of ceratopsians, while pterosaurs rode warm air currents overhead. This planet had been honing its forms for over 165 million years, far from fading, actually cresting in variety and vitality. The dinosaurs held no inkling of replacement. They weren't flawed branches heading toward doom. Instead, they stood as the pinnacle of big terrestrial vertebrates the Earth had ever fostered. They had ample cause to assume their supremacy would endure forever. Nearly, it didn't. In our history, the extraterrestrial stone obliterated it all. But in this evening's alternate path, the projectile plunked innocently into the Pacific, letting the dinosaurs rouse to another day of their 165-million-year routine. So, what might they have achieved with 66 million more years to evolve? What forms could they have taken? To grasp that, we must recognize a truth beyond their awareness. Transformation loomed on the horizon, not abrupt or devastating, but gradual and relentless across scores of millions of years. The cozy, even-keeled warmth of the Mesozoic drew to a close. A prolonged chill approached, spurred by drifting plates, emerging peaks, and shifting sea flows that would one day encase Antarctica in frost. Fresh flora emerged too, grasses that would blanket the lands and reshape every habitat in their wake. The dinosaurs confronted trials unseen in their 165 million years of development, pressures that would probe their flexibility far beyond any single impact. Before diving in, though, let's examine the roots of their supremacy and why mammals lingered in obscurity. The explanation isn't the usual one. A familiar tale circulates in documentaries and school books, a tidy account for today's landscape. It claims the dinosaurs were sluggish, chilly-blooded flops, doomed lineages ruling merely because superiors hadn't arrived. They were oversized and simple-minded, chained to basic drives, ill-equipped for shifts. The space rock merely swept away obstacles for the rightful successors. Mammals, with their hot blood and smarts, poised in the background for their rise. The wipeout served as a kind favor, a vital reboot, letting evolution correct course. This tale is mostly fiction. Seeing its flaws is key to fathoming a dinosaur-surviving world. Far from flops awaiting ousters, they were an evolutionary marvel of immense scale, possibly the top large land vertebrate dynasty ever. They commanded ground habitats for over 165 million years. Let that sink in. Modern human anatomy dates to about 300,000 years ago. Our whole Homo lineage, kin and all, stretches to roughly 2.5 million years. Dinosaurs outlasted that by 66-fold. They branched into countless varieties, claiming every imaginable role, from pint-sized bug munchers to 40-ton leaf grazers, spanning all continents, thriving in everything from steamy jungles to icy poles. And right up to the impact, they betrayed zero hints of waning. In fact, the variety of dinosaurs kept growing. The final phase of the Cretaceous era wasn't a time of stagnation for these creatures. It was their pinnacle. So what kept mammals so diminutive? Why, despite sharing the planet with dinosaurs for 150 million years, did they fail to evolve beyond the size of a badger? The classic explanation is straightforward. Dinosaurs held them down. The prime habitats for large animals were dominated by massive dinosaurs, leaving mammals unable to vie for them. They got pushed to the edges, into darkness, into tunnels and branches, high above where the colossal beasts couldn't reach. Eliminate the dinosaurs, and mammals would surge into all that empty territory. This idea has an obvious charm. Yet, newer studies indicate it's at most partial and maybe even reversed. Research from 2021 by scientists at Oxford and Birmingham universities examined the evolutionary pressures on various mammal lineages before and after the KPG extinction, employing advanced stats to pinpoint where each branch encountered ecological barriers. Their discovery was eye-opening. The forebears of today's placentals and marsupials, the lineages that later spawned whales, elephants, and humans, weren't mainly clashing with dinosaurs. They were getting edged out by fellow mammals. The Mesozoic era wasn't solely populated by the little shrew-like forms we typically picture as primitive mammals. It featured an astonishing array of mammalian branches, nearly all now vanished. Multituberculates, Gondwanatheres, Eutriconodons, Dryolestids. These beings had already seized numerous slots for small to medium builds. Certain ones glided, others swam, burrowed, or sported dentition tailored for smashing tough nuts, carving flesh, or pulverizing vegetation. The precursors to contemporary mammals weren't restrained by far-off dinosaur behemoths. They were surpassed by nearer kin, other mammals far better suited to Mesozoic environments. Consider the implications for this alternate scenario. With the asteroid averted, dinosaurs persisted. True, but those rival mammal factions endured too. Multituberculates, which in our history outlasted the mass die-off and lingered another 30 million years before fading, would have stayed in rivalry with rodent forebears. Gondwanatheres would have held sway over spots that marsupials could have claimed in the southern continents. No wipeout of competitors occurred. The mammal stocks destined to yield elephants, primates, and humans would have lingered in the same evolutionary bind they'd known for 150 million years. Squeezed overhead by dinosaurs and laterally by their peers. But let's probe further. Let's explore why dinosaurs excelled at gigantism to begin with. The response uncovers a core limitation shaping our hypothetical path. Dinosaurs possessed a breathing apparatus that mammals could never rival. Similar to today's birds, which are essentially avian dinosaurs, they used one-way airflow across stiff lungs, bolstered by air sacs permeating their frames, including bones. Mammals inhale and exhale via the same route, blending oxygen-laden air with depleted CO2 heavy stuff. It's wasteful. Dinosaurs, however, directed air steadily over oxygen transfer zones, pulling in vastly more per inhalation. That's how birds soar above Everest's summit as mammals wheeze below. It's why sauropods hit 50 tons while top terrestrial mammals cap at 20. Dinosaurs didn't merely fill big animal roles, they were biologically primed for scale. Their bones were hollow and pneumatized with air chambers linked to lungs, yielding frames lighter yet sturdier than any mammals. They matured swiftly, hitting full size in mere years instead of decades for equivalent mammals. Egg-laying freed them from lugging embryos internally. A gestating sauropod defies physics, yet an oviparous one could yield scores of young annually. Their entire physiology was fine-tuned for niches they'd mastered over 165 million years. Any mammal aspiring to large grazer status here would confront foes that outdid in oxygen uptake, maturation speed, breeding pace, and weight efficiency. Mammals as a whole weren't lesser. They just played under rules tilting toward another blueprint. Place mammals into the void created by the KPG extinction event. Allow them 66 million years free from rivals, and they would give rise to creatures like elephants, whales, and massive ground sloths. But with dinosaurs still present, mammals would stay confined to their familiar niches. Tiny, active at night, and pushed to the periphery of ecosystems. This alternate timeline unfolds in just such a reality. Not one where dinosaurs are delicate survivors barely hanging on, but a realm where they reign supreme over every land-based habitat. Their evolutionary edges render them nearly invincible in the roles they've claimed. Mammals, meanwhile, find themselves hemmed in by relentless rivalry on all fronts. Dinosaurs didn't claim their supremacy through chance or mere circumstance. They earned it through sheer excellence in their adaptations. That close asteroid brush wouldn't have altered any of that. Yet this is where the narrative takes a fascinating turn. Dinosaur rule rested on a bedrock of steady, balmy conditions that defined the entire Mesozoic era. For 165 million years, Earth functioned as a vast greenhouse, balmy from equator to poles, moist, blanketed in forests, and marked by minimal shifts in seasons. Dinosaurs arose and thrived in this environment, perfectly tuned to its demands. They had no exposure to glacial epochs, no encounter with open plains, no taste for the sharp climatic upheavals that defined the emerging Cenozoic. Profound transformations loomed on the horizon, challenges dinosaurs had never confronted. Land masses were shifting into fresh arrangements, carving out sea passages that would reshape global ocean flows. Antarctica was pulling away from South America, and soon enough a chilly stream would encircle the southern continent, trapping it in isolation and blanketing it with frost. The Himalayas were set to thrust upward as India collided with Asia, their eroding stones pulling CO2 from the air and driving planetary chill. Vast grasslands were poised to unfurl over land masses, birthing novel habitats and intense, new evolutionary demands. Dinosaurs had demonstrated unrivaled command of the Mesozoic. Our speculative history now probes whether they could have conquered the Cenozoic as well. A harsher, thirstier, more fluctuating domain, laced with extremes unlike anything in their deep past. This era would probe their flexibility far beyond what the asteroid might have wrought, calling for breakthroughs their ancestry had never necessitated. They possessed 66 million years to rise to the challenge. Let's explore how they might have seized the opportunity. A decade of millions of years has elapsed since the asteroid's near miss. If you could venture into this era, the differences might escape you initially. The land masses have barely budged. Plate tectonics crawls at centimeters annually, so 10 million years brings only subtle geographic tweaks. The weather persists as warm, damp, and equatorial even in polar zones. Lush woodlands still span from one end of the globe to the other, thick, verdant, and saturated with dampness. At a casual look, it echoes the Cretaceous landscape we departed. Still, evolution never pauses, even amid apparent stability. 10 million years stretches vast, outlasting the full run of the Homo genus, surpassing the gap from primitive tools to today's devices. No species holds steady across such eons. They evolve, refine, niche down, and branch out. The dinosaurs inhabiting this post-asteroid interval wouldn't mirror their Cretaceous forebears exactly, regardless of the world's surface-level continuity. The real transformation during these years wouldn't center on the dinosaurs per se, but on the vegetation they relied upon. Flowering plants, or angiosperms, had been proliferating through the Cretaceous, outcompeting the ancient conifers and ferns that once ruled Mesozoic woodlands. Absent the extinction's chaos, this expansion would have pressed forward without interruption. Angiosperms boasted traits ensuring their takeover was all but certain: swifter breeding, accelerated change, and tight bonds with pollinators and seed carriers. By 10 million years after our point of departure, they would have overtaken the bulk of global woodlands, with many now producing fruit. Fruit stands as one of nature's master strokes, a plant's enticement to beasts. Consume this sugary, nourishing pulp it offers and transport my seeds afar inside you, then release them amid nutrient-rich waste, granting them an advantage right from the start. This tactic proves wildly effective, explaining its repeated emergence across plant groups. In our history, the surge of fruit-producing plants during the early Cenozoic era spurred the development of fruit-eating mammals, including the primates that ultimately led to humans. In this alternate scenario, a similar chance arose. Yet the creatures most primed to take advantage of it weren't mammals at all. They were dinosaurs, specifically the maniraptorans and theropods, encompassing groups like dromaeosaurids, troodontids, oviraptorosaurs, and the forebears of today's birds, displayed traits that would prove ideal for thriving in fruit-abundant woodlands. These included dexterous hands for handling items and clinging to limbs, plus forward-directed eyes offering stereoscopic sight to accurately gauge distances while snatching edibles or jumping across boughs. Being compact and lightweight, they could scale trees and perch on slender branches that would buckle beneath bulkier dinosaurs. Certain ones, especially the oviraptorids, had developed beak-like mouths without teeth, perfectly adapted for handling fruits and seeds. Imagine one such descendant, 10 million years along in this alternate path. A creature roughly the scale of a present-day howler monkey, adorned with vibrant plumage for warmth and showiness. Its forelimbs preserved the three-fingered clawed heritage from theropod kin, but they've grown even more agile for precise tasks. The beak sports a modest curve at the end, handy for ripping into rind-covered produce. It dwells high in the treetops of blooming woodlands, bounding between perches and feasting on the angiosperm riches. Naturally, this is imaginative conjecture. We can't pinpoint the exact evolutionary outcomes in a divergent history, but it's rooted in authentic patterns from evolution, drawing on features already evident in Cretaceous maniraptorans and genuine environmental openings. Those blooming woodlands would favor any group able to capitalize on them, and the petite maniraptorans and theropods held a clear edge over the era's mammals. However, transformations wouldn't be limited to the upper levels. On the woodland ground, the major Cretaceous plant eaters would keep evolving, adjusting to shifts in their vital flora. The hadrosaurids, those duck-billed dinosaurs, boasted the most advanced foliage-milling apparatus among any dino group. Vast arrays of meshed teeth in perpetual renewal, grinding hardy greens with unmatched prowess. As angiosperms proliferated with varied consistencies and nutrient mixes, hadrosaurids would evolve in tandem. Certain branches might specialize in specific flora or locales, while others turn versatile, succeeding on diverse forage. The essential truth is they wouldn't stagnate. Evolution presses on relentlessly. The ceratopsians would also keep branching out. By the late Cretaceous, they'd split into numerous forms across North America and Asia, ranging from spaniel-like to pachyderm proportions, with a dazzling array of horns and frills. Absent the mass die-off, this variety would burgeon further. Some offshoots could grow massive, claiming roles later taken by elephants and rhinos in our world. Others might shrink, gaining agility for varied surroundings or diets. And the sauropods, the Jurassic's iconic long-necked behemoths that appeared to wane in variety by the late Cretaceous, would endure too. As high-browser experts tapping unreachable greenery, they'd remain relevant wherever lofty woods stood. Our timeline's catastrophe erased them before their adaptability could unfold. Here, they'd demonstrate their resilience. 10 million years after the asteroid strike, the landscape would feel familiar to a Cretaceous observer, yet altered in countless subtle shifts. Fresh species replacing the familiar novel habits, fresh interspecies ties, innovative shapes in emerging roles. Dinosaurs weren't morphing due to a hostile planet pushing them. The globe stayed balmy, verdant, and essentially Mesozoic at heart. They were evolving simply because that's life's essence, probing options, occupying voids, branching into multiplicity. Yet the profound shifts loomed ahead. Approximately 55 million years ago, Earth stood on the brink of an extraordinary shift. A rapid and intense surge in warmth was imminent, driving worldwide temperatures to heights unseen for tens of millions of years. The Paleocene-Eocene thermal maximum, or PETM, loomed ahead, posing challenges to the dinosaurs unlike any they'd encountered previously. The key uncertainty was their preparedness for it. Some 55 million years back, an astonishing alteration gripped the planet's climate. Over a mere 20,000 years, a mere instant on the geologic scale, global heat levels jumped by 5 to 8 degrees Celsius. The polar areas, mild compared to today, turned outright balmy. Palms sprouted in Alaska, while crocodilians lounged along the Arctic Ocean's edges. Even the ocean depths heated up by a few degrees, reshaping currents and sea life across the globe. Experts dubbed this episode the Paleocene-Eocene thermal maximum, or PETM, ranking it among the sharpest climatic upheavals in the past 100 million years of Earth's story. The trigger likely stemmed from a huge influx of carbon into the air. It could have arisen from eruptions tied to the North Atlantic's formation, or the breakdown of seafloor methane hydrates, or maybe a mix of the two. Whatever the source, it sparked a greenhouse surge fiercer than anything the dinosaurs had faced since the Triassic. This event served as a profound trial. In our real history, it profoundly influenced mammalian development. Numerous species vanished, while survivors often dwindled in size since compact forms shed heat more readily. Fresh branches of life emerged, tailored to the steamy environment. Primates destined to evolve into monkeys and apes showed up in fossils precisely then, as though the heat wave unlocked fresh niches amid the chaos it wrought. In this alternate scenario, that very same upheaval would have struck. The PETM arose from deep Earth dynamics unrelated to the asteroid strike, thrusting dinosaurs rather than mammals into the fray. And, fascinatingly, dinosaurs may have held an edge in enduring such blistering conditions over mammals. Consider the biology behind it. Mammals are endotherms, producing their own warmth inside and striving to hold a steady core temperature, typically near 37 degrees Celsius. This demands heavy metabolic effort and relies on advanced ways to cool off, perspiring, heaving breaths, hiding in shadows, or limiting movement to chillier hours. Yet when outside air nears or tops that internal level, those tactics falter. In scorching heat, a mammal battles basic physics, attempting to offload warmth into a world unwilling to take it. By contrast, big dinosaurs likely functioned as gigantotherms. Their enormous bulk kept internal temperatures fairly even, no matter the surroundings. Much like a vast reservoir that resists quick changes in heat. They generated far less internal warmth than mammals, drawing from sunlight by day and holding onto it overnight. Without the need for mammals' elevated, steady temps, they faced less risk from overheating in a warming world. Smaller dinosaurs brought their strengths too. Feathers clad many, offering flexible protection. They could puff out to hold warmth in the cold or flatten to vent excess in the heat. What aided their endurance through polar chills before might have shielded them from equatorial swelters amid the PETM. Even dinosaurs could find the Eocene's tropical belts taxing, possibly spurring shifts toward higher latitudes or forging barren zones near the equator, too harsh for sizable creatures. The poles, though, would have turned into havens, balmy, humid, blanketed in dense woods reaching almost to the Arctic and Antarctic rings. Ideal terrain for dinosaurs large and small, venturing into once fringe territories. Yet evolution wasn't confined to dry land. The seas buzzed with change, too. Our imagined history would boast a feature absent from reality: the ongoing saga of Mesozoic ocean giants. In the actual past, mosasaurs and plesiosaurs perished at the KPG line, felled by the disaster that doomed their terrestrial kin. The voids they abandoned got claimed later by whales, which arose from terrestrial mammals through the Eocene, one of nature's grandest makeovers. However, in this alternate history, those marine reptiles didn't vanish. They were already dominating the available ecological spaces when the PTM dramatically altered marine environments. The mosasaurs from the late Cretaceous were thriving at their height. Enormous aquatic lizards, with some stretching up to 15 meters long, equipped with formidable jaws and flipper-shaped limbs. As top hunters in the coastal waters, they mirrored the positions held today by great white sharks and killer whales. Had the extinction event not occurred, their evolution would have pressed onward. Certain branches could have developed sleeker forms, gaining speed and superior skills for pursuing fish and squid across vast open seas. Additional lines might have bulked up even more, capitalizing on the plentiful ocean bounty during the Eocene hothouse. Meanwhile, the plesiosaurs, those peculiar elongated-necked sea creatures that had endured for more than 135 million years until the asteroid wiped them out, would have forged ahead on their bizarre developmental path. Their design, featuring 4 broad flippers and a neck surpassing the full length of many fellow creatures, appears downright odd and inefficient by contemporary standards. Still, it proved effective enough to carry them through the Jurassic and Cretaceous eras. In the Eocene's heating seas, certain plesiosaur groups might have refined their predation tactics, transforming those extended necks into surprise attack tools that lunged at fish groups from surprising directions. Other variants could have shifted to filter feeding, sifting plankton from the balmy currents much like baleen whales do now. Ultimately, the seas in this imagined scenario would have diverged sharply from those in our real past, rather than whales, dolphins, and seals, all stemming from terrestrial animals that reinvaded the water. We'd witnessed the ongoing expansion of groups that had been fully oceanic for hundreds of millions of years. Comparable habitats would exist, yet the creatures inhabiting them would seem utterly alien. Along the shores where continents kissed the waves, pterosaurs would have flourished too. In our reality, they perished with the dinosaurs, ceding the air to avian successors. But here, they endured, and the Eocene's balmy, nutrient-rich waters would have suited them perfectly. Envision a pterosaur rivaling a light aircraft in span, gliding above equatorial seas and snatching surface fish with a beak as long as a person's arm. Imagine flocks of tinier pterosaurs breeding on ocean bluffs, taking on the niches seabirds claim in our timeline. See the Eocene skies divided between pterosaurs and birds, both rooted in dinosaur ancestry, yet so distinct in build and background that they'd vie for certain spaces while partitioning the rest. The Eocene hothouse endured for eons, giving natural selection ample time to craft myriad adjustments to its climate. By roughly 50 million years ago in this parallel world, dinosaurs would have achieved a stable balance with their steamy surroundings, spreading across all land masses, ruling most ground and sky domains, and coexisting in the seas with their reptilian aquatic relatives. To anyone watching then, it might have felt like the natural order. Dinosaurs as enduring as the planet's peaks and oceans. Yet climates never remain static. While dinosaurs reveled in their balmy paradise, the forces unraveling it were already stirring. India's collision with Asia was thrusting up the Himalayas, and the erosion of those fresh peaks would start pulling carbon dioxide from the air. Antarctica was inching toward the South Pole, paving the way for a novel current to cut it off from tropical heat. The extended chill was on the horizon, set to reshape the planet more drastically than any space rock. That heat wave was temporary. About 34 million years ago, our world embarked on a gradual descent into cooler times, leading eventually to the Pleistocene's glacial epochs. Antarctica sparked the shift. For ages, the southern landmass had linked to South America via a slim isthmus, allowing tropical currents to temper its edges despite the latitude. As the plates separated, though, the Antarctic circumpolar current emerged, sealing the continent away from global warmth. Vast ice caps formed there for the first time in hundreds of millions of years. The Earth's climate dial had been lowered, with no full reset in sight. The changes spread from the poles. Worldwide temperatures plunged by a few degrees. Ocean levels dropped as moisture froze into Antarctic glaciers. As climate gradients between the equator and poles intensified, precipitation patterns altered dramatically. Those vast forests, stretching from pole to pole, which defined the dinosaur era, started to withdraw. This marked a novel shift. For roughly 150 million years, stretching back before the earliest dinosaurs roamed, the Earth functioned as a true greenhouse. It stayed humid and temperate, blanketed in greenery from Arctic realms to Antarctic expanses. Dinosaurs arose within this environment, proliferated across it, and dominated every landmass under its influence. Never before had they encountered a world where vast ice caps blanketed substantial land areas, where winters turned brutally severe, or where woodlands yielded to entirely different ecosystems. The Oligocene chill presented an unprecedented trial for them. Yet at this point, it's essential to dispel a widespread misconception. We often view dinosaurs as denizens of the tropics, beings tied to balmy environments that would falter in chilly settings. Popular images show them basking in misty jungles, their enormous forms basking under an ancient sun's rays. And parallels to today's reptiles seem to bolster this idea. Snakes and lizards struggle in frosty zones, absent from places like Antarctica. But this notion is likely entirely misguided. Evidence reveals that dinosaurs thrived in polar territories throughout the Mesozoic. Discoveries of dinosaur fossils in Alaska and Antarctica come from sites at latitudes enduring extended winter nights and frequent sub-zero chills. These weren't fleeting intruders or strays. They formed stable communities, nesting and nurturing offspring in environments we'd deem unforgiving today. The renowned Prince Creek Formation in northern Alaska captures a varied dinosaur community from around 70 million years past, featuring hadrosaurs, ceratopsians, and tyrannosaurs, all enduring the full year beyond the Arctic Circle. What enabled their survival? The solution lay right on their hides: feathers. For years, scientists have recognized that numerous dinosaurs sported feathers. This wasn't limited to petite avian theropods. It spanned a broad array of forms. Feathers appear on tyrannosaurs, ornithischians, and creatures of all sizes from various branches of the dinosaur lineage. Their initial role wasn't for soaring through the air. It was for warmth. These structures developed to retain heat close to the body, enabling dinosaurs to stay mobile in weather that would force a bare-skinned reptile into dormancy. In this alternate history, such traits became vital amid the global downturn. Feathered theropods, armed with evolution's finest thermal barrier, could venture into cooler territories as glaciers encroached. Envision a group of mid-sized theropods, their forms cloaked in dense feathering that stirs in icy gusts, pursuing prey over wintry terrain. Unimaginable in the Mesozoic, these beings would appear strikingly avian, for they were, in essence, ground-hunting birds that never abandoned terrestrial pursuits. Bigger dinosaurs confronted distinct hurdles. A 15-meter sauropod couldn't depend on feathers for warmth like a 2-meter theropod might. Their body proportions didn't allow it. Yet gigantothermy has dual edges. The sluggish heat shifts that aided colossal dinosaurs through Eocene warmth would similarly buffer them against milder frosts. Their enormous frames altered temperature so gradually that brief icy spells barely impacted them. They could have undertaken seasonal journeys, tracking milder zones and sustenance, much like today's big mammals. Alternatively, they might have confined themselves to equatorial bands, yielding polar areas to tinier, more versatile kin. Ornithischians, ceratopsians, hadrosaurs, and ankylosaurs raise a fascinating puzzle. No firm proof shows they had feathers, though certain fossils hint at filament-like coverings that could have offered comparable benefits. Within our speculative scenario, the demands of dropping temperatures might have spurred denser, more protective integuments in these groups. Imagine an Oligocene ceratopsian, its frame sheathed in a heavy layer of proto-feathers, its grand frill scaled back from the ornate flare of Cretaceous forebears, now sleeker and more efficient against the bite of winter. It might resemble a woolly rhinoceros, yet retain the iconic outline of a horned dinosaur. Still, the deepest transformation lay not with the dinosaurs but their surroundings. With the onset of cooler, drier conditions, the unbroken woodlands fragmented. Certain baseline warmth and moisture levels are vital for trees to flourish. As those ideal conditions shifted southward toward the equator, The woodlands followed suit. Emerging in their stead were expansive terrains. Scattered woodlands with openings amid the trees, grassy fields, and sunlit glades piercing through to the soil below. These weren't the vast prairies that would eventually redefine the globe, yet they marked the onset of a significant shift. The era dominated by dense forests was fading, giving way to the rise of unobstructed expanses. For species of dinosaurs that had thrived in wooded environments for 150 million years, this represented a dramatic overhaul of their surroundings. The fundamentals of staying alive were evolving. In a thick forest, concealment offers protection. Predators can launch surprise attacks, or prey can evade detection by remaining hidden. Bulk plays a smaller role than cunning camouflage, and quick bursts matter less than agile navigation through the undergrowth. Yet in exposed terrains, hiding spots vanish. Survival hinges on outpacing threats to flee, possessing the mass to confront them head-on, or maintaining sharp awareness to detect peril in advance. Forming herds proves beneficial, since collective vigilance outperforms solitary watchfulness. Endurance for covering great distances gains precedence over brief dashes. These very dynamics in our history molded mammalian lineages, yielding the swift equines and gazelles, the canine packs and feline hunters that came to rule open habitats. Within this divergent history, identical forces would have molded dinosaurs accordingly. The outcomes could have mirrored those familiar forms closely, not through any transformation into mammals, but because parallel environmental challenges often yield convergent adaptations. A swift plant eater remains swift regardless of whether it's an equine or an ornithomimid. A group-stalking carnivore stays one, be it a lupine or an advanced theropod. The Oligocene served as a pivotal phase, linking the lush, temperate woodlands of the Eocene to the impending savannas. The dinosaurs that navigated this period would have diverged markedly from their Cretaceous forebears, more resilient to cooler climates and barren vistas, starting to hone traits essential for the emerging landscape. They had weathered their initial severe trial, though the deeper metamorphosis lay ahead. Approximately 23 million years ago, an unassuming lineage of vegetation launched an expansion that would redefine every landmass, save Antarctica. The proliferation of grass stood poised to upend the world. At first glance, grass appears unremarkable, a modest, ground-hugging growth that's simple to dismiss. We tread upon it, trim it back, and scarcely notice its presence. Yet from the early Miocene onward, around 23 million years ago, grass embarked on a takeover that altered terrestrial landscapes more profoundly than any cosmic catastrophe. In its wake, it blanketed about 40% of Earth's dry land, spawning novel biotic communities absent throughout the prior 400 million years of terrestrial existence. Grasping grass's transformative power requires recognizing its unique biology compared to other flora. Typical vegetation elongates from its apex. Harm the crown of a shrub or tree, and you cripple its growth, potentially dooming it outright. Grass, however, originates anew from its roots. Shear it, scorch it, or crop it to the quick through foraging, and it rebounds from the base. This renders grass nearly impervious to destruction by grazing or flames, akin to the mythical Hydra, sprouting fresh heads upon decapitation. Moreover, grass incorporates silica phytoliths, tiny crystalline shards within its structure, lending it a resilient, gritty texture that's hard to break down. Creatures attempting to consume it essentially gnaw on grit, eroding their dentition with each mouthful. In our era, such traits spurred the development of hypsodont dentition, the tall, perpetually renewing molars seen in equines, bovines, and fellow grazers. Those unable to adapt to grass's rigors found themselves excluded from these burgeoning prairie realms, barred from a premier ecological bounty. The advance of these grassy domains stemmed from the ongoing chill and aridification that commenced during the Oligocene. With diminishing precipitation in heartland regions, woodlands withdrew to humid zones along shorelines and waterways. The voids they left filled with grass, not out of any preference for aridity, but due to its superior endurance in suboptimal zones where arborescent life faltered. In essence, grasslands embody hardy opportunists among plants, claiming the fringes that elude other species. During our timeline, Miocene meadows ignited a spectacular burst of mammalian innovation. Equines transitioned from diminutive woodland foragers into the robust, fleet-footed browsers of today. Ruminants, such as bovines, cervids, and gazelles, proliferated rapidly. Their intricate, multi-compartmented digestive systems, enabling them to derive sustenance from fibrous fodder, indigestible to most other beasts. In response, carnivores adapted in kind, honing skills to pursue and subdue in these altered domains. The forebears of wolves and large felines grew swifter, more pack-oriented, and finely tuned for pursuing game across expansive music landscapes. Today's African savanna, teeming with wildebeest and zebra throngs, lion prides, and wild dog packs, represents the peak of 20 million years of development in grassy habitats. Within this alternate scenario, those grasslands would have expanded precisely as in our own past, since the climatic forces behind them were independent of the creatures inhabiting the land. The key distinction lies in dinosaurs rather than mammals, confronting the demands of this transformed environment, with evolutionary pressures mirroring those we know. Graze on the vegetation, or perish, sprint with agility or fall victim, detect threats early or end up as dinner. The outcomes, shaped by the unyielding forces of natural selection, would probably resemble familiar patterns closely. Take the ceratopsians, those iconic horned dinosaurs that ruled the plant-eating roles in late Cretaceous North America. Amid woodland settings, they foraged as browsers, snipping foliage with parrot-style beaks and grinding it via slicing dentition. Yet such teeth weren't suited for grasses, which would erode them rapidly due to their silica-rich fibers, impairing effective foraging. Those ceratopsians enduring in a grass-filled realm would be the ones devising fixes for this issue. A plausible route, developing perpetually regenerating teeth, akin to those in rodents or equines. Dinosaurs already possessed the genetic foundations for ongoing tooth replacement, evident in the stacked dental arrays of hadrosaurs where fresh teeth continually emerged from beneath. A ceratopsian branch acquiring genuine continuous growth dentition could have grazed without limit, grinding against the abrasive plants while replenishing its teeth endlessly. Envision a Triceratops offshoot, advanced by 20 million years beyond its Cretaceous roots. It retains its ceratopsian essence. The core form proves too effective to discard, though its build has shifted. The skull stretches longer and dips nearer the earth, optimized for low-level cropping instead of high browsing. The beak broadens into a squared shape, built to shear grass in wide sweeps, functioning like a biological mower. The neck frill diminishes, shedding rolls in showiness or heat control, with resources redirected to powerful chewing muscles for tackling fibrous greens. It roams in vast groups, numbering in the hundreds over Miocene plains. A surging mass of muscle and horns sweeping the terrain much like wildebeest, traversing the Serengeti. Yet feeding on open ground invites hazards. Dense woods offer cover from hunters, but vast flats expose you from kilometers off. Survival hinges on watchfulness, group size, and quickness. Herding among Miocene ceratopsians would prove indispensable, not merely advantageous. An isolated forager on such exposed turf spells doom. 1,000-strong collective, with eyes everywhere on the skyline, stands a fighting chance. The ornithomimosaurs, Cretaceous-era ostrich-like dinosaurs, came equipped with traits, priming them for prairie existence. Blessed with speedy gaits, elongated limbs, and slender frames, they likely dabbled in omnivory, tapping diverse sustenance. Across boundless steppes, they could fill niches akin to antelopes or gazelles. Nimble, watchful, clustered in bands, banking on velocity to evade attackers. Picture a Miocene ornithomimid. Its limbs extend further than forebears, its form aerodynamically honed for prolonged dashes over level expanses. The neck reaches high to peer above the grasses, catching signs of peril from afar. It sustains on blended fare, grass seeds, bugs, and minor vertebrates, an adaptable menu suiting rugged zones beyond narrow feeders' reach. In peril, it hits 60 kilometers per hour bursts, outpacing chasers dependent on straight-line chases. It dwells in bands of scores, and a single alarm triggers a chain reaction. The group erupts in flight, confusion rippling outward, quicker than foes can close in. Hadrosaurs offer a compelling example. Their advanced tooth batteries, layers of interlocking hundreds, formed the pinnacle of dinosaurian plant-milling tech. They were somewhat primed for grazing already, managing abrasive foliage that stumped rival browsers. In this speculative path, hadrosaurs might emerge as premier grass-eaters, their built-in edges granting an early lead in the forage race. Still, a stronger bet, aligning with evolution's competitive dynamics, suggests no one group seizing total control. It's conceivable that the Miocene grasslands could have been divided up between various dinosaur lineages, with each carving out its own specialized niche, much like how today's African savanna supports wildebeest, zebras, buffaloes, gazelles, and numerous other animals, all tapping into the grassy expanse in their unique fashions. The ecological landscape had transformed entirely. The wooded backdrop that once framed the Mesozoic saga was dismantling, giving way to vast expanses of swaying grasses beneath a boundless sky. Fresh opportunities awaited any creatures ready to adapt their ways. Dinosaurs had honed their skills in forested realms over 150 million years. Yet now they might have just 20 million years to conquer an utterly foreign existence. A key concern remained. What threats would pursue them? In realms of swift-moving herds, predators too would need to evolve. Tyrannosaurus rex reigned as the ultimate hunter in the late Cretaceous. 12 meters of raw muscle and skeleton, 6 tons of lethal might, jaws capable of crumpling a vehicle. It excelled at overpowering big game through sheer dominance, within the Mesozoic woodlands where stealthy approaches thrived and victims had no warning until the strike. This approach shone brilliantly. T-Rex commanded its trophic level for eons, unchallenged and apparently flawless. Yet flawlessness depends on context. Shift the surroundings, and it turns to irrelevance. The sweeping Miocene plains would have posed a dire challenge for a traditional tyrannosaur. In dense woods, a 6-ton beast could lurk among trunks, closing in undetected, until the final lunge. Out in the open, concealing a 4-meter-high at the hip monster proves impossible. Prey spots the danger from kilometers off. When it nears attack range, the targets are fleeing, and your bulky frame with its stubby limbs can't pursue. That said, the Tyrannosaur branch wouldn't simply vanish. Evolution clings to proven designs. Still, adaptation was essential, and its course becomes clear from parallels in mammalian carnivores under similar strains. Miocene grassland tyrannosaurs likely would have grown sleeker. Survival would reward those quicker, less hefty, superior at sustained chases. Across millions of years, T-Rex's stout form would elongate and slim down. Limbs lengthened against body size, stance more level for stability during runs, possibly a reduced skull to lighten the forward load. The outcome could resemble an enlarged take on primitive tyrannosaurs like Dong or Guanlong, far slimmer than their bulkier heirs. Even a streamlined tyrannosaur, though, would grapple with a core issue. The biggest quarry would form herds, and solo strikes on such groups are risky and wasteful. A solitary wolf fails against a prime bison. A lone lion shuns a mature buffalo. The quarry's size, ferocity, and protective allies make it too formidable. The fix, honed separately by wolves, lions, and African wild dogs, lies in teamwork. Packs collaborating to separate, tire out, and subdue targets beyond anyone's solo reach. This raises a fascinating puzzle about dinosaur habits. Evidence on whether big theropods packed up is inconclusive. Track sites hint at group travel. Fossil clusters mix hunters with victims. Yet interpretations vary. Certain paleontologists argue tyrannosaurs socialized for the hunt. Others see them as loners, uniting only for feeding scraps or mating. Without definitive proof, we draw from ecosystem logic. That logic points to grassland tyrannosaurs evolving pack tactics inevitably. Not due to some grassland charm, but because tackling massive, risky herd-based dinosaurs demanded it. Few other methods could succeed. The evolutionary push would be relentless. Cooperators feasted. Isolates famished. Through deep time, such forces could rewire instincts. Enlarge intellects for teamwork and signaling. Forge societies absent in prior eras. Imagine a Miocene tyrannosaur pack, say 6 to 8 members, traversing the plains at dawn's glow, leaner than Cretaceous forebears, perhaps 7 meters long, rather than 12, 3 tons over 6, yet swifter, nimbler, synced in ways T-Rex never required. The pack has detected a group of ceratopsians feeding on the grass, far off, and they're fanning out now, some veering broadly to block potential retreats, while the rest advance straight on to herd the animals into the trap. Their assault isn't the brute force of one massive beast, but a synchronized assault from various directions. Every member understands its part, collaborating to topple quarry that no single one could handle by itself. Yet tyrannosaurs weren't the sole theropod group reshaping themselves for the prairies. The diminutive hunters, dromaeosaurids, troodontids, and fellow maniraptoran theropods, evolved in parallel, occupying varied slots in the emerging ecosystem. In certain respects, these compact carnivores were more primed for open-field pursuits than the tyrannosaurs. They were swift sprinters from the start. Fossil records suggest many operated socially, in packs. They possessed dexterous hands for handling items, eyes angled forward for sharp binocular vision, and brains notably sizable for their frames. Such features would thrive amid the grasslands. Dromaeosaurids, the slashing raptors made iconic by Jurassic Park, seemed especially fitted for team takedowns across vast expanses. As pursuit specialists, they excelled in velocity and nimbleness. Those signature curved claws likely helped secure victims as their mouths inflicted fatal wounds, a method amplified when several assailants strike at once. Within this imagined history, dromaeosaurid branches could have branched out to mimic roles of today's African wild dogs or wolves. Endurance chasers that wear down targets over distance instead of surprise lunges. Picture a troop of 2-meter-long dromaeosaurids, their plumage streaked to blend seamlessly with the savanna. They operate in bands of 20 or so, signaling via vocalizations and postures, synchronizing efforts over miles of unobstructed land. Their approach is straightforward yet potent. Select a victim, chase relentlessly until fatigue sets in. Rotate who harasses while companions recover. It's akin to tactics employed by contemporary wild dogs, ruthlessly efficient against speed-dependent herbivores. No creature sustains top pace indefinitely. In time, weariness prevails. Troodontids offer the most captivating prospect. These were dinosaurs' cleverest thinkers. Slender theropods boasting the highest brain-to-body proportion among their kind. Their capabilities merit deeper examination later, but as prairie stalkers, they'd prove adept, likely targeting overlooked small game and fostering advanced group dynamics, unmatched by kin. In this revised timeline's Miocene grasslands, the landscape served as a deadly arena overseen by hunters of all sizes. Dominating were leaner tyrannosaur groups, Earth's premier terrestrial carnivores still, yet profoundly altered after 50 million years of environmental pressures. Midway roamed dromaeosaurid squads, exhausting quarry via unyielding stamina. At the base, troodontids and kindred minor theropods pursued fare from tiny mammals and bugs to one another. The era of isolated titans was fading. The lone tyrannosaur's dominance through raw might yielded to a fresh paradigm. Carnivores triumphed via teamwork, synchronization, and maybe the seeds of what we'd term tactics. In realms of exposed fields and watchful groups, intellect grew as vital as muscle. This prompts a long-standing paleontological puzzle. With sufficient epochs, another 50 million years, for instance, might dinosaurs have attained genuine smarts? Might they have cultivated intellects able to grasp reality, strategize ahead, even ponder their own being? The response proves more nuanced than expected. Back in 1982, Canadian paleontologist Dale Russell unveiled a conceptual exercise that evolved into one of speculative paleontology's most renowned and divisive works. Russell was examining Troodon, a late Cretaceous theropod famed for its oversized brain in proportion to its build. Observing the upward trajectory and neural capacity for this line, Russell posed a straightforward query. Imagine if dinosaurs had avoided extinction. What could the offspring of Troodon, that clever little theropod from the late Cretaceous, have turned into over an additional 66 million years of evolutionary development? Russell's response was the dinosauroid, A speculative being that walked on its hind legs, featured dexterous hands with thumbs that opposed the other fingers, and sported a spacious, dome-shaped skull able to accommodate intellect on par with humans. He went so far as to have an artist craft a model of this dinosauroid, yielding something eerily human-like. Eyes directed straight ahead, an erect stance, and a physique reminiscent of a classic extraterrestrial more than any reptile from the Mesozoic. The message rang out plainly. With sufficient time, dinos might have developed smarts akin to ours, potentially rivaling us on this planet. This dinosauroid concept fired up widespread fascination, yet fellow paleontologists panned it right away, and the backlash has grown sharper over the ensuing years. The core issue isn't pondering smarter dinosaurs. That's a fair guess backed by fossil data. Rather, it's the leap that brains always push toward a human-shaped form. Russell's logic boiled down to, smarts need big brains. Big brains demand a vertical stance to steady them atop the backbone. A vertical stance frees up the front limbs from walking duties. Freed front limbs morph into handy manipulators. Thus, any bright species ends up humanoid-ish. Appealing as that sounds, it's likely flawed. Think of today's sharpest non-human minds. Ravens and parrots show smarts matching those of chimps and gorillas. They wield tools, crack tough puzzles, spot their reflections, and grasp ideas like consequences flowing from actions. Still, they resemble us not at all. Feathered flyers with bills and frames honed by 150 million years of avian adaptation. Their cleverness arose despite a form worlds away from bipedal primates, and those limits didn't block their path to brilliance. Or, take octopuses, masters of mazes, tool users, and seemingly endowed with unique temperaments. No creature strays further from human contours. 8 limbs, boneless build, a spread-out brain with nerve cells in every arm. Nevertheless, they rank as Earth's top invertebrate thinkers, maybe top thinkers overall. The takeaway: evolution isn't aiming for intelligence as some endgame. It's just another adaptation, like fangs, flight, or poison, that arises when environments reward it. And it can bloom in nearly any chassis, since cognition boils down to handling data, not needing thumbs or two-legged gait. So how might brainy dinosaurs have appeared in reality? Most likely, still dinosaurian. In this imagined history, the troodontids after 66 more million years would remain identifiable theropods, clinging to the blueprint that fueled their forebears' success. Two-legged strides, a level-oriented build, counterweighted by a lengthy tail, clutching forelimbs, a snout lined with fangs. The real shifts would occur within the cranium. Troodon's noggin was already outsized among dinos. Its encephalization quotient, the gauge of brain volume against body mass, surpassed all other recorded dinosaurs. Should the forces from the last segment keep boosting mental prowess, say for synchronized group predation, sharper recall in vast plains, or tracking kin in intricate herds, then Troodon brains could have kept swelling. To what extent? Hard to pin down precisely, but avian survivors of the wipeout offer hints as the sole dinosaur branch to persist. With brain-to-body scales like those of apes, corvids, and psittacines hit that mark in about the 66 million years we're projecting for our alt-history troodontids. Given Troodon's head start, it's plausible they'd match that benchmark. Envision a troodontid from, say, 10 million years back in this parallel world, perhaps amid a lush Miocene landscape, stretching roughly 2 meters nose to tail end. Its plumage shifts from dorsal grays to ventral whites, ideal blending for prowling open meadows. Prominent eyes gaze forward for top-notch depth perception. Its paws hold 3 hooked digits, nimble enough to seize and finesse items beyond its Cretaceous kin's grasp. Moreover, the brain within its prominently bulging skull represents the biggest relative to body size among all terrestrial creatures on the planet. This being possesses intelligence, though far from human caliber. We'll explain the distinction shortly, but cleverness that's crucial for enduring. It operates in groups ranging from 10 to 20 members, and the synchronization during those pursuits is extraordinary. They execute side attacks, distracting strategies, and even intentional ruses where certain members pretend to be hurt to draw targets into traps. The animal employs basic implements like branches to poke into dens for concealed quarry or stones to smash tough-shelled edibles. It boasts an intricate array of sounds featuring scores of unique vocalizations that convey details on threats, feeding spots, and group hierarchies. Juvenile troodontids acquire skills by observing and copying their seniors, going beyond mere innate responses. In numerous respects, this organism would fill a role in the ecosystem, akin to today's wolves or primitive hominids. As a pack hunter, its triumphs hinge more on intellect than raw power, more on teamwork than solitary might. It would prove daunting, versatile, and equipped to flourish in diverse habitats worldwide. Yet it wouldn't construct urban centers, invent scripts or arithmetic or deep thought, or ponder the cosmos or its own cosmic role. What stopped it? Human-like cognition demands not merely an enlarged mind, but a precise confluence of conditions that, based on evidence, happened solely once across Earth's biological chronicle. Such intellect arose in primates, whose forebears had already devoted tens of millions of years to forging elaborate social bonds. Dexterous limbs shaped for clutching limbs and minds honed for traversing multidimensional spaces. Subsequently, their forebears descended from arboreal homes to the African plains, confronting fresh evolutionary demands, scavenging sustenance in harsh terrains, collaborating within bands, sharing nuanced data on provisions and perils. Over mere millions of years, their neural capacity surged, fueled by a cycle, linking societal intricacy with mental prowess. This progression relied on innumerable elements, each vital, yet insufficient alone. Primates colonized Africa, yet despite 3 ventures into North America, no branch there grew expansive intellects. Open plains emerged across continents, but solely in Africa did they yield a being of conceptual reasoning. Some form of smarts may abound cosmically, but our brand, enabling invention, inquiry, and reflection, could be exceedingly scarce. These hypothetical troodonids might achieve cleverness on par with ravens, cetaceans, or great apes. They could wield implements, build intricate communities, and transmit wisdom across eras. However, the ignition that propelled our lineage from shrewd primates to inquisitive beings might elude any saurian branch, regardless of evolutionary span. Dinosaurs might spawn thinkers, but not inquirers into thought itself. Still, that constraint offers a peculiar solace, implying our imagined history would leave the world untamed, stunning, fierce, and wholly unconcerned with purpose. A realm of beasts behaving as beasts must, devoid of observers to deem it sublime or horrific or to query its intent. Saurians would dominate for 230 million years, unopposed and unchronicled by any recorder of their reign. In such a reality, no entity would lament our absence, for none would conceive of our potential presence. About 2.5 million years back, Earth passed a pivotal mark. The extended chill, initiated in the Oligocene, which had reshaped lush woods into milder groves and those into steppes, at last culminated. Glaciers started forming in the north, not merely atop remote summits, but sprawling over vast lands, entombing Scandinavia and Canada beneath kilometers of iced mass. The Pleistocene era dawned, ushering in a climatic pattern unseen for over 250 million years. The frost didn't surge forward and halt. Rather, it ebbed and flowed, pushing ahead in glacial phases enduring about 100,000 years, pulling back in warmer interludes spanning 10,000 to 20,000 years. Across the Pleistocene, over 20 such oscillations unfolded. Each altered the globe's landscapes, driving biomes equatorward, before permitting recovery, forging and erasing continental connections, compelling organisms to evolve or perish. In our history, that period gave rise to the famous megafauna of the Ice Age. Woolly mammoths with their dense fur and sweeping tusks, woolly rhinoceroses resembling armored beasts, cave bears reaching 3 meters high when upright, and enormous ground sloths comparable to elephants in size. These species were tailored for icy environments, featuring enormous frames to conserve warmth, heavy layers of fur or blubber for protection, and the capacity to endure meager plant life through extended frigid seasons. They epitomized the wildlife of their epoch. But in this alternate timeline, none of those giants would have appeared. No mammoths, no woolly rhinos, no oversized sloths. Instead, the roles of those big, chill, tolerant plant eaters would fall to entirely different beasts: dinosaurs. The key issue becomes whether dinosaurs could endure the ice ages whatsoever. This represents their ultimate trial, the hurdle that would drive them farthest beyond their familiar evolutionary path than any prior challenge. For 200 million years, dinosaurs flourished in a balmy, humid, tree-covered planet. The open plains of the Miocene marked a notable shift. Yet the climate remained relatively temperate compared to plain extremes. Suddenly, they would confront seasons with lows of -40 degrees Celsius, snow blanketing the earth for 8 months annually, and food so limited that only southward treks or resilience against prolonged hardship could ensure survival. Were they up to it? Evidence suggests they might well have been. Recall the Prince Creek Formation in Alaska, home to dinosaurs that resided full-time north of the Arctic Circle in the Cretaceous. Consider how feathers developed as perfect insulators. Note that numerous dinosaur groups already possess the finest natural gear for wintry climes. Observe that birds, modern dinosaur descendants, excel in Earth's harshest cold spots these days, from Antarctic penguins to Arctic tundra snowy owls. The changes needed for plain life would have been substantial, no doubt. Yet they wouldn't demand that dinosaurs transform into wholly new forms. Rather, they would amplify traits dinosaurs already held. Take the Cereratopsians, the horned plant munchers who had adjusted to grassland existence back in the Miocene. A Plene version would stand as a breathtaking sight. Envision a Triceratops-like form, refined over 60 million years of tougher and tougher settings. It might stretch 8 or 9 meters, padded with hefty fat stores to last through sparse winters. The frill, formerly mainly for show and heat control, would compact and harden into a practical shield, while a plush layer of feathery covering spanned from snout to tail tip. not flashy like a jungle bird's feathers, but the dense, warming down of a survivor in brutal freezes. Imagine one traversing a Siberian steppe in an interglacial thaw, part of a vast herd roaming seas of grass and scrubby bushes. At a distance, it could pass for a mammal with that woolly hide and hulking build, but closer inspection reveals the classic dinosaur outline. Quadrupedal gait, beak-tipped head, brow spikes jutting out. It chomps on hardy, ground-hugging plants, its tooth array pulverizing foliage more effectively than any mammal's setup. As cold grips the land, the group heads south in pursuit of fading heat. Looping back northward once thaws unleash fresh greenery. The hadrosaurs would grapple with parallel demands, probably evolving parallel fixes. Their advanced mouth gear, those racks of hundreds of mesh teeth, would handle rugged northern flora superbly. Long gone were the two-legged forebears. By now they moved mostly on four sturdy limbs with squat, broad torsos wrapped in heavy insulation. During deep winter they'd cluster in sheltered ravines to block biting winds, bunching close for shared body heat, much like present-day musk oxen. Even the hunters would evolve accordingly. A Plene tyrannosaur, tracing back to the Myoene's group-stalking lines, would emerge as a horrifying predator, shorter than Cretaceous kin at maybe 5 meters, but cloaked in pale gray and white plumage that blended seamlessly with snowfields. It would stalk in organized groups, overwhelming outsized targets via strategy and stamina. In the leanest winter stretches, with game hard to find, it could dial down its metabolism into a semi-hibernating mode, relying on fat reserves until spring revived the hunt. Still, not every dinosaur lineage would master the freeze. Certain dinosaur groups would have withdrawn to warmer equatorial regions, enduring in those refuges where climates stayed relatively stable through the peaks of glaciation, isolated for most of the Cenozoic by the Central American Seaway. South America could have turned into a haven for archaic species, offshoots of Cretaceous survivors untouched by the need to cope with chill or open plains, lingering in lush tropical woodlands as though frozen in time, akin to living relics. Comparable sanctuaries would have existed in Southeast Asia and Central Africa, isolated pockets of mild warmth amid a world growing ever colder. This would have carved Earth into distinct climate bands, more pronounced than at any point since dinosaurs first roamed. Within the equatorial belts, echoes of the ancient Mesozoic era could have lingered. Humid, tree-covered landscapes teeming with dinosaurs that might have seemed recognizable to any time traveler from the Cretaceous. Farther north and south in the temperate and icy expanses, entirely novel forms would have arisen. Dinosaurs reshaped over 60 million years to thrive in environments their forebears couldn't have foreseen. As altered from Tyrannosaurus and Triceratops as woolly mammoths, diverged from their warm climate elephant forebears. Those ice ages would have acted like a forge, challenging dinosaurs with harsher trials than the prior 200 million years of their reign. Certain branches would have faltered under the strain, vanishing as shifting weather exceeded their tolerances. Others would have endured, toughened by the repeated freezes and thaws, prepared for future upheavals. In our actual history, what followed was humanity, a shrewd primate emerging from Africa, conquering the world, driving megafauna to oblivion, altering habitats and forging societies capable of reflecting on Earth's ancient past. But in this imagined path, such a creature never arose. The precise circumstances that sparked human cognition, the unique chain of developments in African primate lineages, would have unfolded otherwise or not emerged. The Pleistocene would have drawn to a close with no observers to label it. Yet the glacial rhythms would have persisted, waxing and waning every 100,000 years. Through every such shift, the dinosaurs of this chilled globe would have shifted ranges, evolved and persisted, just as they had weathered all prior planetary ordeals. After 230 million years, they stood as unparalleled masters of endurance. The frost posed merely another hurdle. One they overcame. Biology features a principle known as Bergmann's rule, straightforward in its essence. Among members of a species or evolutionary line, those in cooler areas grow bigger. The basis lies in physics. Bigger bodies offer a lower surface-to-volume ratio, slowing heat loss. In frigid settings, size confers benefits. It helps conserve warmth better. It allows greater fat stockpiles to outlast scarcities. It enables withstanding hardships that would doom tinier creatures. Bergmann's rule molded the megafauna of our Pleistocene. Woolly mammoths outstripped their equatorial kin in stature. Cave bears loomed far larger than today's brown bears. Ireland's giant deer sported antlers stretching 3.5 meters, exaggerated, almost cartoonish in scale, yet borne by frames robust enough to support them. Harsh cold bred titans. In this alternate scenario, the principle would have held true. Yielding, colossal beings of another sort. The ceratopsians roaming Pleistocene steppes might have ranked as the biggest in their group since Cretaceous times or bigger still. A mature specimen could span 10 meters from snout to tail tip, rise 2.5 meters at the shoulder, and tip the scales at 8 or 9 tons. Its horns would likely have been briefer than Triceratops, simpler and more practical, for warding off threats and vying for partners rather than the flashy adornments of old. Its frame would bulk out into a rounded barrel, stuffed with fat layers and gut chambers for breaking down vast hauls of poor forage in the short Arctic summers, then drawing on reserves through endless winters. These beasts would travel in vast herds that blotted out the skyline, not mere scores or hundreds, but thousands strong, endless streams of muscle surging over mammoth plains, timed to the yearly surge of greenery. During peak warmth, they would venture into the far north, the high Arctic, munching the burst of growth, fueled by non-stop sun. As cold gripped, they would pull back southward, clustering in sheltered vales with shallower drifts and lingering forage. The magnitude of these journeys would astound, millions traversing thousands of kilometers in unison, ranking among the world's premier natural wonders. Hadrosaurs would have claimed those same grasslands, their numbers possibly surpassing even the ceratopsians. Their specialized dental batteries provided a key advantage for grinding down the most fibrous plants, while their capacity to switch between bipedal and quadrupedal movement could have offered practical benefits during heavy snowfall, allowing them to stand upright and reach into bushes and short trees when snow covered the lower plants. Imagine a Pleistocene hadrosaur stretching 7 meters in length, its frame enveloped in a thick layer of feathery filaments that held body heat close to the body, its broad duck-billed mouth designed for snipping plants near the icy surface. It travels amid a blizzard alongside a group of hundreds. The herd huddles tightly to share heat. their exhalations creating misty plumes in the biting cold. Yet, the northern steppes represented just one facet of the tale. The Pleistocene era formed a mosaic of varied landscapes, each fostering its distinctive array of dinosaurs. Beringia, the isthmus linking Asia and North America amid ice ages, likely served as a major route for dinosaur dispersal, much like it did for mammoths and people in our reality. Creatures originating in Asia probably migrated to the Americas, and the reverse, resulting in overlapping wildlife across the northern landmasses. Siberian tyrannosaurs would have been close relatives to those in Alaska, linked by mere thousands of kilometers of unbroken terrain. Mongolian ceratopsians might have intermixed with their Wyoming counterparts. This setup could have formed one vast interconnected biome, extending from France to Florida, bound together by the chill. Deeper into southern latitudes, the equatorial refugia would have safeguarded entirely dissimilar relics. Within the Amazon basin, the Congo, and Southeast Asia, remnants of ancient woodland ecosystems endured the Ice Age swings, shielded by their position near the equator, despite the glacier's overwhelming northern zones. In these areas, you could encounter dinosaurs resembling their Cretaceous forebears, sauropods grazing amid the treetops, petite theropods pursuing game in the dense undergrowth, a realm largely untouched by the passage of time. Such refugia acted as biodiversity havens, safeguarding bloodlines lost in other regions and acting as origins for repopulating vacated lands as glaciers withdrew. The carnivores thriving in the icy realms matched their quarry in grandeur. The cooperative pack-hunting tyrannosaurs from prior discussions would have hit their zenith during the Pleistocene, their group dynamics polished through eons of natural selection, their tactics for the chase sharpened to a fine art. Witnessing a band of Pleistocene tyrannosaurs overwhelming an adult ceratopsian would reveal a display of orchestrated ferocity, certain members hurting the target, others blocking paths to safety, while more lay in wait. The entire team operating with an accuracy reflecting inherited skills handed down through family lines. Lesser carnivores occupied diverse roles. The dromaeosaurids, those agile, feathered chasers, likely roamed the wide steppes in groups numbering up to dozens, wearing down medium-sized targets via relentless pursuit. Lone stalkers could have prowled woodland borders, striking suddenly from concealment. Meanwhile, the troodontids, those big-brained, tool-using predators from Chapter 9, may well have emerged as the era's most flexible hunters, adept at capturing varied victims via smarts, teamwork, and flexibility. The oceans hosted their distinct Pleistocene inhabitants. By this point, the mosasaur and plesiosaur lines had branched into numerous forms, occupying slots from shore-based piscivores to vast pelagic behemoths, traversing the same chilly seas that sustained whales and seals in our history. Certain varieties may have evolved hefty blubber reserves for warmth, mirroring the forms of sea mammals. Some could have turned into migratory wanderers, trailing food sources across warm and cooler seas seasonally. The biggest heirs to the Mesozoic's mighty ocean reptiles might have approached whale dimensions, sifting krill and tiny fish from the rich waters near the poles. The recurring Ice Age fluctuations established a pattern of growth and shrinkage, of species loss and new forms arising, of fitting in and adjusting anew. Every glacial push drove animals equatorward, splitting groups and opening doors to variation. Every thaw enabled resettlement of fresh territories, reuniting once isolated clusters. Across more than 2 million years, this cyclical force accelerated evolutionary change, generating variety and refinements at speeds uncommon in the planet's past. In this imagined history, the Ice Ages spared the dinosaurs no ruin. Instead, they reshaped them utterly. They compelled these creatures to develop answers for challenges unknown to their forebears. They adapted their forms and habits to endure environments utterly alien to the balmy Cretaceous era of their origins. These colossal beings of the icy realms mark the pinnacle of 230 million years of dinosaurian development. Not a finale, but merely the most recent installment in an enduring epic. Then came the present interglacial period. Glaciers withdrew, warmth returned. Vast steppe landscapes yielded to woodlands and frozen plains. The resulting planet, our contemporary one, bore the imprint of 66 million years of events absent from our own history. A planet where dinosaurs remained the dominant force. Imagine yourself atop a ridge in this alternate now, surveying the vista. The terrain feels recognizable. Identical peaks, waterways, and shorelines as in our reality. Plate tectonics unfold over eons, and 66 million years falls short of remaking land masses on a grand scale. Africa abuts Europe, forming the Mediterranean Sea. India has fused with Asia, thrusting up the Himalayas. The Americas span from Arctic to Antarctic, linked by Central America's slender isthmus. It's the very atlas from your childhood lessons. Yet the creatures inhabiting it are wholly transformed. Join me on an expedition across this reimagined globe, region by region, habitat by habitat. Discover the fruits of 230 million years of ceaseless dinosaur progression. Begin in Africa's East African savannas, home in our world to the planet's densest gatherings of big beasts. The features birthing the Serengeti persist here unchanged. Those fertile volcanic grounds, the rhythmic rains, the boundless plains fading into infinity. But rather than wildebeest and zebra throngs, you'd encounter flocks of ceratopsians, their crowned skulls nodding while they feed, clad in light, feathery coverings tuned for equatorial warmth. Certain kinds would tower elephantine, claiming the role of colossal plant eaters. Lighter and swifter variants would band in vast groups, depending on alertness and sheer volume for safety. Carnivores would mirror roles, though their shapes diverge. Squads of mid-sized theropods, tracing back to tyrannosaur or dasplitosaurid roots, would scour herd peripheries for the frail, the juvenile, the stragglers. Their tactics, refined across epochs alongside their quarry, would gleam with cunning. A few might chase quarry across vast distances, akin to wild dogs of the plains. Others could lurk in ambush amid high grasses, exploding into action the instant victims strayed near. Overhead, the savanna airspace teems with pterosaurs. Not the behemoths of old, but compact forms reshaped for today's demands, stepping into slots held by vultures and hawks in our era. Certain ones scavenge, wheeling over carcasses before alighting to strip remains bare. Others hunt keenly, plummeting toward diminutive targets with falcon-like accuracy. Birds soar alongside, naturally. The sole dinosaur branch to weather the actual cataclysm, now coexisting with pterosaur kin in a realm allowing both to flourish. Sail westward over the Atlantic to South America, where novelty awaits. That landmass lingered apart through much of the Cenozoic, fostering oddities in our history. Enormous sloths on the ground, horrifying flightless avians, bizarre ungulates unique to its bounds. Here, seclusion instead birthed singular dinosaurs. Sauropods might linger, their elongated necks still foraging amid Amazonian woods, an archaic design shielded in this isolated haven. Or fresh dinosaur branches could arise, shapes foreign to every other shore, born from scores of millions of years apart. Australia veers even more bizarre. Our world's seclusion there spawned marsupials and monotremes, beasts diverging from placental kin elsewhere. In this variant, the continent sealed off with its dinosaur residents circa 45 million years past, when it parted from Antarctica. Those original inhabitants would diverge utterly, since yielding oddities as startling to us as the platypus or kangaroo. Lacking precise knowledge of the split's dinosaur roster, we speculate on their appearances only to affirm their distinction from global kin. Eurasia and North America, the northern realms, would brim with the prairie dwellers outlined in this account. Vast herds of hadrosaurs would roam the plains. Packs of tyrannosaurs and dromaeosaurs would hunt together with strategy and precision. Troodontids would employ tools and thrive in intricate social structures. The wildlife would shift depending on latitude and weather patterns. Lush southern tropics would transition into milder wooded areas, open prairies, and eventually icy northern tundra. Yet the core group of creatures would remain familiar throughout this vast supercontinent. The seas would belong to marine reptiles. By this point, mosasaurs and plesiosaurs would have evolved into countless varieties, occupying every ocean habitat from shallow shores to deep waters. Certain types would be compact and nimble predators of fish, weaving through seaweed beds and vibrant reefs. Larger ones would act as enormous sieving feeders, gliding through nutrient-rich polar regions with wide-open jaws, sifting out krill and tiny fish, much like baleen whales in our history. The biggest could match the blue whale's scale, 30 meters in length, weighing 150 tons, the most enormous creatures to ever exist, their forms buoyed by the surrounding water, which would pulverize them on dry land. Nowhere on this alternate planet would you spot a single human. No urban sprawl on the skyline, no highways slicing through the savannas, no vessels on the waves or plains overhead. No cultivated fields, no barriers, no tamed beasts obeying people's orders. The earth would feel untamed in a manner untouched for 10,000 years in our reality. Maybe even more primal than anything our world ever knew, since early humans altered landscapes with hunting and controlled burns long before farming began. This void would transform every aspect of the globe's dynamics. Free from human predation, megapredators would flourish far beyond their numbers in our era. Ceratopsian groups across Africa could swell to tens of millions strong, their total mass surpassing any mammalian assemblage we've witnessed. Lacking human disruption to split environments, habitats would span whole landmasses unbroken, enabling vast journeys and genetic exchange on levels our altered landscapes can't support. Absent human-induced losses, global diversity would soar, not merely due to dinosaurs' presence, but because the chain of disappearances, triggered by people in our history, would never occur. The world's atmospheric balance would differ as well. Without combustion of ancient fuels, without excess carbon released into the air, without warming risks upheaving the weather. The 2026 version of this alternate Earth would remain locked in the Pleistocene glacial rhythm, approaching a new peak freeze in several millennia. Its temperatures dictated by planetary orbits and eruptions, not factory outputs. Dinosaurs would confront that impending chill, just as they had all before, via relocation, physiological shifts, and the steady churn of evolution. Gazing upon this realm, one might wonder, is it superior to ours? Does a dinosaur-dominated existence outshine human rule? Such a query defies simple resolution. Superior in whose eyes? Dinosaurs would likely favor their domain if they could form opinions. Mammals denied their ascent might beg to differ. The Earth itself stays neutral, a sphere of stone, liquid, and gas, unconcerned with the life forms scurrying over it. Still, there's merit in a realm steady for 230 million years, one where no lone species remolds the entire living sphere for its convenience, where biological change unfolds naturally, fueled by weather shifts, rivalries, and random events, not the calculated designs of an advanced society. Such a place holds a certain unspoiled essence, though none might be present to value it. Dinosaurs never sought dominion over the planet. They merely adapted to the environments they encountered, and they continued adapting as those environments evolved. They endured cosmic strikes and lava floods, cold epochs and hot surges, the bloom of angiosperms, and the expansion of grassy expanses. They embodied supreme versatility, the foremost endurers, the branch that endured whatever challenges the world hurled their way. In our history, a celestial boulder concluded their era. In this parallel path, no such force arose. Today, the world is theirs as it has been for 230 million years, with none to challenge that claim. This whole series has explored dinosaurs, their potential descendants, their adjustments, the shapes they'd take to occupy today's roles. But one issue lingers unexamined, one that could have lingered in your mind from the start. What became of the mammals? In our history, the dinosaurs' downfall handed mammals their golden era. For roughly 150 million years, these creatures had skulked in the margins, tiny and largely active only at night, squeezed into overlooked habitats that the dinosaurs ignored or simply couldn't access. Everything changed when the asteroid struck. The non-avian dinosaurs perished, leaving the landscape eerily vacant. In our history, mammals surged forward into that void, branching out to claim every possible role in the ecosystem and giving rise to an astonishing array of species, from minuscule shrew-like animals to enormous whales, from tunneling moles to flying bats. Just a mere 10 million years post-catastrophe, they had claimed dominion over Earth. Yet in this alternate scenario, no such window opened for them. The dinosaurs endured, keeping mammals tucked away in obscurity. Still, obscurity isn't oblivion. Mammals wouldn't have vanished entirely. They'd have persisted much as they did across those prior 150 million years, compact, elusive, thriving modestly within their restricted domains. Across the ensuing 66 million years of uninterrupted development, they could have branched out further, but only within those boundaries, occupying spaces the dinosaurs left untouched. Nocturnal life would have been their stronghold. Despite their vast variety, dinosaurs were likely diurnal, rousing in daylight and resting come nightfall. Clues indicate that early mammals honed their endothermic systems and sharpened senses precisely to capitalize on the dark hours, preying on bugs and dodging reptilian hunters under cover of night. In this divergent path, that domain would stay firmly in their grasp. As twilight fell over the forests of today's world, a flurry of diminutive, furred beings would stir, pursuing prey, scavenging and carrying out their full existence in the fleeting span from evening to morning. The subsurface realms would fall under their sway as well. Excavating suit smaller frames. The effort to burrow escalates sharply with body mass, and mammals had been digging since the Mesozoic era. In this imagined history, a whole concealed biosphere could thrive just below the dinosaurs' tread. Interconnected burrows and layers housing mammal kinds that seldom, if ever, emerged topside. Such underground dwellers might have cultivated extraordinary traits: superior auditory detection for pitch-black navigation, ultra-sensitive vibrissae for probing passageways, shrunken vision, or outright sightlessness. They'd remain unseen by the overhead behemoths, forming a clandestine society, oblivious to the surface overlords. The upper branches of trees would provide yet another sanctuary. Agile climbers like small mammals could scale where bulky dinosaurs faltered. The lofty layers of a lush jungle canopy might prove virtually free of reptilian intruders. A tangled realm of twigs and foliage, reachable solely by lightweight beings nimble on slender boughs. Within this alternate reality, mammal forms akin to primates could arise. Limbs with opposable digits and eyes oriented forward, tailored for navigating the intricate, vertical labyrinth above. Technically, they wouldn't qualify as true primates. That evolutionary line might have veered sharply elsewhere. But they'd occupy parallel roles, potentially mirroring key features via parallel selection. Might cleverness have emerged in these furtive mammals? Conceivably, yet it's doubtful to reach great heights. The forces that forged human smarts were unique: existence on the open plains of ancient Africa, the demands of foraging over broad expanses, benefits from group dynamics and basic implements. Such dynamics wouldn't press on pint-sized night dwellers evading dinosaurs. At best, their wits might parallel those of today's raccoons or rodents, shrewd, versatile, adept at puzzles, though the flame of advanced awareness akin to ours could remain unignited. Yet consider this intriguing angle. Mammals could have carved out victories in a domain dinosaurs scarcely mastered, the expansive seas. In our timeline, cetaceans like whales and dolphins sprang from terrestrial forebears who re-entered aquatic life about 50 million years back. They claimed supremacy as major hunters and plankton strainers in contemporary waters, stepping into vacancies left by vanished seagoing reptiles. Under this alternate scheme, those slots would go to mosasaurs and plesiosaurs, though maybe not everyone. Those reptiles needed air and hugged the shallows. Constrained in dive depth and submersion duration. A mammalian branch geared toward profound immersion, evolving exceptional lung capacity and resilience to crushing depths like today's whales, could tap into depths beyond reptilian limits. The abyssal ocean, that immense shadowy expanse beneath the illuminated zone, might evolve into a mammalian frontier. Envision one such being in the murky deeps of this reimagined now, a warm-blooded mammal, tracing lineage from some modest forebear that ventured seaward amid dinosaur land dominance. Roughly dolphin-sized, perhaps, with a sleek form built for fluid motion. Its flippers, evolved from ancient limbs, allow swift navigation through the water, while a dense blubber coating keeps it warm against the chill. It forages in the deep scattering layer, a bustling zone teeming with organisms far below the waves, plunging for over half an hour at a time on one lungful of air, relying on echolocation to track down meals amid pitch-black void. Up in the brighter shallows, mosasaurs prowl the sun-drenched seas, yet in these frigid depths, shrouded in obscurity, The mammal reigns unchallenged, dominating an underwater domain the reptilian giants never mastered. All this remains pure conjecture, naturally. True knowledge of mammalian evolution in a dinosaur-dominated world eludes us. Still, the core idea holds. Evolution would have progressed regardless. Life persists, as the old adage reminds us, not by any enchanted mechanism, but via the straightforward process of genetic diversity and natural selection. Whatever ecological gap arises will sooner or later draw an occupant. Mammals would have carved out roles beyond the dinosaur's grasp, branching out to claim those untapped opportunities. They wouldn't have claimed dominion over the planet. That honor stayed with the dinosaurs, unbroken for 230 million years. Yet mammals would have endured, evolved, and thrived. They might have ruled the fringes, commanded the hidden corners, forming a rival lineage flourishing in the overlooked realms of the reptilian overlords. In this imagined timeline, mammals dodged extinction entirely. They simply never seized the spotlight, and maybe in the shadowy woodlands and profound seas of that parallel planet, they linger even now poised in the gloom. Consider this intriguing notion to ponder. If these words reach you, if you grasp their sense, then the asteroid struck home. That's the central irony woven into this whole hypothetical scenario. Envisioning a reality where dinosaurs outlasted their fate demands an imaginative intellect, and yours, that very essence, owes its presence to the dinosaur's downfall. Human smarts aren't evolution's predestined pinnacle, a goal life inevitably chased. They're a fluke, a chance occurrence, the unlikely fruit of a precise chain of happenings, kicked off by a cosmic boulder slamming into the Yucatan Peninsula 66 million years back. Had that rock veered off course, no soul would muse on alternate paths. This isn't a claim. Intelligence couldn't have surfaced in our hypothetical world. We've touched on the troodontids, those big-brain theropods potentially honing smarts akin to today's corvids or cetaceans. We've pondered the Mayanes pack hunters, those communal carnivores that could have refined advanced signaling and teamwork. Some form of cleverness would likely have budded in the dinosaur lineage eventually. It's far too advantageous to ignore when environments reward it. But the profound awareness we possess, self-reflective thought that ponders its origins, probes reality's secrets, and marvels at the universe's expanse, that's a whole other realm. Human self-awareness sprang from a unique confluence of factors. Our forebears were primates, a group refined over millions of years with intricate social bonds, dexterous limbs, and minds tuned for spatial challenges in treetop worlds. Then shifting climates drove them from woodlands onto Africa's open plains, imposing fresh demands that boosted group dynamics, signaling, and foresight. In mere millions of years, our cerebral capacity ballooned, fueled by a cycle of escalating social intricacies and mental prowess unmatched elsewhere in terrestrial life's saga. Each phase hinged on chance. Without primates venturing to Africa, sans that timely environmental shift, or, if our kin had tackled the grasslands differently, the result could have diverged wildly. Cleverness might have arisen, yet not the sort that constructs observatories, crafts films, or speculates on bygone eras. In the alternate history, those pivotal twists wouldn't align. Primates might have vanished altogether or stayed diminutive arboreal folk, never touching Earth. Dinosaur supremacy could have choked the grasslands, barring room for an ambitious primate to innovate. The exact stressors that birthed human awareness would never converge. Thus, no being would pose the very query on your mind. What if history had veered otherwise? Yet, here's the key insight I'd like you to carry away. Lacking intellect akin to ours doesn't diminish that other world. It doesn't render it inferior, hollow, or devoid of purpose. It simply renders it distinct. Being different doesn't equate to being lesser. The imagined alternate Earth from this documentary would brim with breathtaking splendor and intricate wonders. Vast groups of ceratopsians streaming over plains like vital currents. Squads of feathered hunters pursuing prey through clever teamwork and smarts. Seagoing reptiles gliding across seas untouched by trawls or slicks of crude. Pterosaurs gliding effortlessly on updrafts over peaks never scaled by foot. A tapestry of life's varieties, conflicts, and astonishing endurance unfolding on a landscape largely unaltered across 230 million years. Such a realm wouldn't require our gaze to hold value. It wouldn't demand a sentient witness to imbue it with purpose. It would just exist, much like our own planet teems with organisms. Every creature shaped by eons of natural selection, each flawlessly suited to its role. Each woven into a network of connections too vast for any intellect to grasp entirely. We often view awareness as evolution's pinnacle, the aim life's been chasing from that primordial cell, splitting in some primordial sea. Yet that's merely our prejudice, the innate bias of sentient creatures to prioritize cognition above all. Natural selection lacks direction. It has no endpoint. It's merely a mechanism, mutation, survival, transmission, unfolding across immense spans, yielding forms that endure and propagate amid shifting circumstances. The dinosaurs weren't flops for lacking our brand of intellect. They were triumphs, extraordinary and unmatched, ruling Earth for 165 million years, while spawning heirs that still command the heavens. Had the asteroid missed their triumphs would persist, molding themselves to the world's trials, branching into open habitats, thriving, perishing, and transforming, all without a single query about existence. Perhaps there's merit in that simplicity. In a reality that merely persists, free from self-awareness, unencumbered by significance, spared the human urge to probe, rationalize, and defend. A place where existence unfolds, sans the question of purpose. The impact came, the giants fell, and now, 66 million years on, you're hearing tales of a realm that might have been. But as slumber nears, picture it vividly. The humid veil of a Mesozoic evening. Echoes of beasts rustling in the woods, constellations turning above. The very same lights gracing our nights. The identical lunar glow. The eternal ballet of the universe, indifferent to the forms it overlooks. In that reality, repose claims something as well. A dino-kin, nestled in its burrow or sentinel over its group, or adrift in abyssal depths. Eyes shut, respiration easing. Its thoughts, if such they be, fading into quiet. Parallel realms, twin paths. Dusk settling equally upon them. Dinosaurs never pondered their being. They spared no thought for the cosmic stone that could have doomed them, or the paths not taken. They simply endured.